Hello guys, good day again. So let's have an introduction to radiation and nuclear physics and its medical applications as well. So I am a medical physicist. I did my master's in the USC Graduate School, MSc in Applied Physics, major in medical physics. And I attended some residency for radiation oncology medical physics at the USC hospital. Okay, so let's now discuss what is radiation. So we define radiation as energy traveling through a space or a medium. So there are different types of radiation. Even the sound is a form of radiation because sound is an energy traveling through a medium. But what we are going to talk now are non-ionizing or ionizing types of radiation. So um, radiation can be categorized as ionizing and non-ionizing. So ionizing means it cannot ionize from the word itself. It cannot, it cannot produce ions. It cannot destroy DNA. It cannot destroy chemical bonding. But if you talk about ionizing radiation, if a molecule is being hit by an ionizing radiation, it can damage the molecule. It can knock off electrons. So usually the molecule or the element is neutral. But if you remove an electron, it becomes positive and negative. So you produce two charges. You produce ions. You produce positive and negative ions. That's why it's called ionizing radiation. Okay, so what are the examples of ionizing? So we have X-rays, gamma rays, some part of UV, and proton type of radiation can be ionizing, particle type of radiation, neutron that are fast moving, very high speed neutron. Electron can also be ionizing, fast moving. Okay, what about non-ionizing? Non-ionizing radiation, these are radio frequency from your cell phones. It cannot cause DNA damage. It doesn't ionize your DNA. Ultrasound, although it's not electromagnetic, it's mechanical type of radiation. Ultrasound is non-ionizing. Okay, what else? Visible light is non-ionizing. So if we're being hit by visible light, like here, don't worry about cancer or whatever. It doesn't produce ionization. So it's non-ionizing. Okay, so let's go now. There's a nice photo here about the separation of ionizing and non-ionizing. So as you can see here, so ionizing here from UV to X-rays and gamma rays. Non-ionizing, visible light, infrared, the electromagnetic waves used in FM and AM, even in your cell phone, microwave, these are non-ionizing radiation. Even your power lines. In the Philippines, we use 60 hertz power line. It produces radiation, but it's non-ionizing. So we are all exposed to radiation, but mostly non-ionizing. Okay, so your wires, if it's connected to there's current, it produces radiation actually, but on the lower spectrum here, on the left side. Okay, so AM, FM, satellite, infrared, non-ionizing. Microwave, the one that you use in heating food, is also non-ionizing radiation. It cannot ionize. Although most of the non-ionizing radiation, the effects are, especially in infrared and microwaves, the effects are heating. Okay, it can cause heating. Okay, even visible. And for UV, that's the part border where you will have ionizing radiation. Okay, so if you're going to look at this figure here, ionizing radiations are radiations of sufficient energy to ionize molecules. Examples are for photons, electromagnetic as well, X-rays, gamma rays. For particle type of radiation, these are fast-moving particles. Examples are alpha, beta, neutrons, and even protons. If it's moving very fast, it can be an ionizing radiation. So let's go back to your electromagnetic waves. So these are lower frequency on the left, and you have longer wavelength. But as you go further to the right, the frequency becomes higher, but the wavelength of light becomes shorter. Can you imagine this is the only part of the electromagnetic waves that we can see. The rest we cannot see, we cannot smell, we cannot detect unless you have a detector. Okay, so now let's go to, so let's define ionization. Okay, so what is happening in ionization? So let's say you have an atom with a nucleus. Let's say you have neutron here, you have proton there. So there can be a lot of them. And then let's say our classical model, right, of an atom. This is your orbit of the electrons. So let's say we have electrons here, so negatively charged, and you have electrons orbiting around, another negative. But what if you have an ionizing radiation hitting the electron? So let's say this can be X-ray, some part of UV, gamma ray, or particle types of radiation, such as even fast-moving electron can be an ionizing radiation. There's also a positive electron we call positron, or a fast-moving neutron, no charge, or a fast-moving proton, and other cosmic radiation, particles. Okay, so these are actually particle type of radiation, and these are electromagnetic waves or a photon. Photon is like a pure packet of energy, no mass. So, since these are highly energetic, this ionizing radiation are highly energetic types of radiation, they can knock off electrons. They can remove electrons out of its orbit. So later on, after the process, the electrons will jump, or not jump, but will be removed from the orbit. And so, this whole atom will be left with an electron. So it will become a positively charged. So you actually produce ions, a negative and a positive ion. So ionization is the process of removing an electron from its orbit, from the outer shell. Okay? So as I've said, radiation is actually all around us. But now let's focus on ionizing radiation. Let me read this. This is a slide during my master's. Radiation is all around us. Everything in nature, every creature, every material contains and always has contained radioactive substances. You are radioactive yourself, and so is your dog, your car, your coffee, your mother-in-law. Everyone, everything has some form of radioactive material. Okay? So you cannot actually escape ionizing radiation because they are all around us. Radioactive substances that emits ionizing radiation is all around us. Okay, banana that you ate for breakfast earlier, banana has a potassium that is radioactive. Let me, so if you have a sensor, let's say a Geiger counter, let's say this is your Geiger counter, and you eat banana, you can actually detect the emission of the radioactive material. If you eat banana, so the banana you can detect it using a Geiger counter. So it's amazing, right? You're actually surrounded. But you know, the levels of these ionizing radiation is low, so we can consider them as background radiation. Everyone is exposed to this background. But if you're exposed more to like artificial sources or man-made or the radiations, the radioactive material that they use in the hospital, these are high intensity or higher activity. I will discuss that later. So there are more emissions on those sources of radiation. So we are not gonna expose ourselves to that unless we need it for medical purposes or medical application. Okay, so let me go back to my slide. So it's everywhere. It's surrounding us. So there's carbon-14. So from the cosmic, from the land, from the plants, eat the food from the cow. They will eat the grasses and they will have carbon-14. So we're gonna eat drink their milk, and then we will have carbon-14 in our body as well. So it's on the water that we drink. It's on there are also other sources from the ground. Uranium is usually the ground, okay, and minerals, and even radon gas from concrete, diba? So my concrete here has some radon gas, but so once in a while we open the window so the radon gas can seep through, but it's very minimal, guys. Okay, but just to tell you, ionizing radiation is all around us. Okay, so if you're going to look, I have a smoke detector. I don't know if you can see it, but there's a smoke detector, and it uses an alpha emitter, radioactive material. So let's go to the different types of radiation. So there is an alpha, which is actually a helium nucleus and with a charge of +2. There is beta, which is actually an electron with a charge of -1, or an antimatter beta, +1. We call it positron, positive electron. And photons. Photons are electromagnetic radiation such as X-rays and gamma rays. So X-rays came from the excitation of electrons. We usually produce it with a machine, right? X-ray machine. And gamma rays, this comes from the nucleus, from radioactive material, from the nucleus of a radioactive material. It has no charge and no mass. Both X-rays and gamma rays have no charge and no mass as compared to particle type of radiation. Alpha, beta, neutron, and proton has mass, okay? Different charges, but all of them has mass, except X-rays and gamma rays. Neutron is a neutral particle. Proton, a particle with a charge of +1, or a hydrogen nucleus. Now we can shield alpha particle with just a piece of paper. Beta can pass through a paper and can be shielded by aluminum, definitely concrete. No? Gamma cannot be shielded by paper, cannot be shielded by aluminum, not much, can still penetrate, and even concrete. So gamma radiation and X-rays can still penetrate concrete, but if you have a steel and especially lead can shield gamma and X-ray radiation. Okay, so let's go back to radioactivity. So radioactivity happens if the nucleus of your radioactive material or the element, the nucleus has proton and neutron, right? To be stable, they should be equal. But if the nucleus and the proton inside the neutron and the proton inside the nucleus is not equal, they become unstable. Okay? A nucleus should contain appropriate number of neutrons to become stable, non-radioactive. That means the nucleus has neutron equal to the number of protons. The number of neutron equals the number of protons, stable. If they are not equal, then they become unstable. So for example, for carbon, okay, the mass number is 12, so the number of neutron and proton is 6. 6 neutron, 6 proton. Non-radioactive, stable. Carbon-13 is still stable, even if it has more neutron now. The proton is 6, the neutron is 7. But as you can see here, this one lacks neutron. So there's an excess of proton in a way. So it's now unstable. If the number of neutron is not equal to the number of protons, they become unstable. Okay, carbon-14 is unstable, carbon-15 is unstable, more neutron, less neutron, less neutron. Okay, an unstable nucleus has too much energy in it. An atom cannot hold this energy forever and it has to be ejected. So isipin nyo, nag-alboroto, I have too much energy. After some time, boom. Sooner or later, the atom must get rid of this excess energy, and that is through an activity, through an emission of radiation, radioactivity. It will emit the excess energy. If it's too much neutron, it will eject or emit the neutron and convert it into another type of particle or a pure energy in the form of, radiation, basically. And then if it emits these excess energy, then it will return to its normal stable state. Something like that. So this is the activity, as you can see here. The activity, the emission of radiation is exponential. So activity now at time t equals the original activity times e raised to the negative t ln of 2 divided by the half-life. Half-life is the time for that radioactive material for its activity to be half of the original. So the time, okay? So it's negative, exponential negative. It means it goes lower and lower. As time passes, the activity of radioactive material becomes lower and lower and lower. Okay? So what is half-life? Half-life is the time it takes for half of the unstable nuclei of the radioactive material to decay. So it means with each half-life, 50% of whatever there is will decay. So let's say time 0. Timer starts now. The activity is 100%. After one half-life, let's say the half-life is 100 years. After one half-life, let's say after 100 years, the activity, the emission of radiation becomes half. So let's say originally it's a tick, 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 tick. After 100 years, it will tick, 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 half of that activity. After another 100 years, half of half, 50% becomes 25%. After another 300 years, 25% becomes 12.5% or 12.5 activity, and so on. So it is exponential. It goes down, 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 exponentially. Okay, so here are some of the half-lives of some of the common radioactive materials. So polonium, krypton, radon, I told you earlier, radon gas, radioactive material, but the half-life is 3.8 days. Strontium, radium, carbon-14. Uranium is used to power nuclear power plants. Some of these can be used as a weapon, which is not a good application of physics, to weaponize. But some of these can be used to treat cancer patients, in research, let's say carbon dating is one very good application because we can determine how long this body, which was found in the mountains of the Alps, in the near Austria and Italian part of the Alps. So one hiker, one time, they hiked the mountains of the Alps and they find this well-preserved, I think 5,000 years old cadaver. It was injured, frozen, and they were able to determine the time of death, 5,000 years, because of the activity of the carbon-14 emitted by the body. And we also have carbon-14 in our body. We can determine it with some Geiger Counter measuring instrument. Okay? So there are different types of radioactivity or the emission of radiation. There's alpha particle emission, beta, and gamma. Okay? So there is what we call alpha decay. So let's say you have a radioactive material, uranium, that's the parent. After some time, it will decay. It will be stabilized a little bit. Yeah. Well, because it's unstable, it will go to its more stable state. Okay, it will emit something, and that is, in this case, alpha. It will emit alpha, and uranium becomes thorium. So this is the parent, this is the daughter. And this is the radiation that it will emit. So nagbabago yung mass number, nagbabago yung atomic number. Ito yung parent, atomic number A, mass number A, atomic number Z. After it undergoes alpha decay, the parent becomes a daughter. The daughter has a mass number of A minus 4 from the original A, and the atomic number is Z minus 2. So 92 becomes 90, 146 becomes 144. This is the daughter plus the alpha that it will be emitted, that it will emit, the alpha particle, which is an ionizing radiation. Okay? So one application, smoke detector. As I've told you, I have a smoke detector. Even I think in your house you have a smoke detector as well. So it's radioactive, but it saves lives. It saves life. So what is happening in smoke detector? You have alpha particles, and this is an electric circuit, closed electric circuit, because it seems charges are flowing because this alpha particles is continuously emitted. But if there's a smoke, the alpha particle will be blocked. And if the circuit is blocked, it will trigger an alarm saying that I am blocked by a smoke. Okay? So don't play with your smoke detector. Just leave it there. Usually there are maintenance. The engineers will come to check on it, but don't play around with your smoke detector. Usually alpha particles are the energy of is deposited in air by a few centimeter. So it cannot, hit you because a few centimeter of air, the energy is already deposited in air. Okay, unless you take out the radioactive material and put it in your skin, so your skin might be injured, or if you inhale it, the membrane of your lungs will be affected. Okay, beta decay. So here you have a parent, let's say thorium. It will decay to a daughter, and it will emit a beta particle. So here, the proton changed, the atomic number is changed, +1. But what is happening here is a neutron is converted into a proton and an electron. So added proton and then emitted electron. We're going to check the balancing of the equation. They're the same. Mass number A, atomic number Z, Z +1, -1, so it's still equal. Okay. Now let's go to gamma decay, gamma radiation. So nothing has changed at the elemental, composition. Like the parent, the daughter is still same element, but with lesser energy because the excess energy is emitted as a gamma decay, lower state energy now. So this is the excited energy state of your parent particle, radioactive material, emits a gamma and then becomes more stable element. Okay. So one application of gamma radiation is in cobalt-60 treatment of cancer patient. So this is a brain, we call it a gamma knife because it melts the tumor using gamma radiation, like a knife, like precise, hits the target and it will kill the cancer cells and it will melt the tumor, like literally. Okay, oops. So take note that this radioactive decay can be a series of decay. So you have a parent, you have a daughter. But thorium is still radioactive, so it still can decay to another daughter, protactinium in this case. And then it can be a series like this. So for example, you have uranium, alpha decays into thorium, and then beta decay into palladium, back to uranium. And then uranium will decay into alpha decay into thorium, chuck, 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 chuck. Look at this table. Chuck, 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 chuck. Chuck, 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 decay into polonium, alpha decay into lead. Finished product is lead. But if you go to another series, like this, gamma, beta decay into beta is blue. Beta decay into lead, but still radioactive lead, so it still decay beta or alpha into mercury, beta decay into thallium, beta decay into lead. So it can be a series of radioactive decay, and every time it decays, it emits either gamma, beta, or beta, gamma, beta, alpha, or even gamma radiation. Okay, so how do we detect it? We use a Geiger counter. I think if you watch it in some movies, tick, 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 there's some sound sometimes. Tick, 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 tick. If there are more radiation, it will tick, 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 tick. Low radiation, tick, tick, tick. So we actually detect it because of its ionization effect. So if you produce ions, this is your radiation, ionizing radiation. If you produce ions on the sensing part of the device, the electron is collected by a lead, a lead, a wire. So on this wire is connected to a counting device or voltmeter. You can measure the collected electrons, the current. Okay, so that's how it works. Now let's proceed to nuclear reactions. So we're done with radioactivity. Nuclear reaction is you actually bombard a nuclei or an element by a, can be a proton, can be a neutron, or can be a gamma radiation. So like hitting something, like a billiard ball, hit something with another something. In this case, nuclear reaction, you can hit it with a nucleon, neutron, I mean, a gamma or a proton. So if you bombard it with a neutron, the boron will become lithium and helium. Okay? A nuclear reaction is said to occur whenever the incident nucleus, particle, or photon causes a change to occur in the target nucleus. Okay, so let's have an example. You have uranium. Now it is being hit by a neutron. So this uranium will become uranium 2, 3, no, it will become barium and it will become krypton. So it will split up. And in the process of splitting up, some of the nucleus are left to free, like they're now free. So take note that one neutron can actually produce more neutron. So it can be a chain of events. You already produce two more elements, and in this example, three more neutrons. So it can be a chain reaction. So one neutron can produce two more. The surrounding uranium can still, this neutron can still hit the surrounding uranium and then produce the same reaction. It becomes a chain reaction. So it can be an uncontrollable process, but for specific application, you have to control that because it will produce tremendous amount of energy and radiation coming out. So in a controlled chain reaction, only one neutron on average causes another neutron to fission or to split up something. Okay, so like in a nuclear reactor, so there are fuel elements, control rods, and moderator. So these control rods are the ones that limits the chain reaction of events. Okay, so this is your core reactor here. So this is a nuclear reactor in a nuclear power plant. So the reactor core is actually composed of the movable rods to limit the chain reaction. So it's composed of water, another water, and water vapor here condensed. So the moderators lose neutrons, and the control rods absorb neutrons. So, oops. Now there are concerns of accident, like the ones that happens in Fukushima and Daiichi, wherein the cooling system was affected by the tsunami, so it got destroyed, and they failed to turn it off or contain it. So if your cooling system is destroyed, then it will just heat up, heat, and then it exploded actually. And some of the radioactive material escaped through the atmosphere to the sewerage. So the whole parts, I think it's like 10 kilometer and later on 1 kilometer radius was evacuated. And you know the radioactive material emitted by this, we even detected it in PNRI. So it was in the news. So you have to be, so then the modern designs of nuclear reactors are actually safer, different design now. So, smaller modular type. And then if there are risk of explosion, earthquake, they are failed to safe. They will, underground, so that no radiation or radioactive material can escape through the atmosphere. So it's safer now. The other type of nuclear reaction, so we have nuclear fission, the splitting up. The other type is nuclear fusion. Fusion, like in Dragon Ball Z, so Vegeta and Son Goku, they will fuse into one element. And in the process of fusion, you produce tremendous amount of energy, usually heat. So let's say you have deuterium and tritium, both hydrogen. Then you are going to fuse them, boom, and they will fuse, and then they will produce tremendous amount of energy. You produce helium and heat, lots of heat. This is the process that what is happening in the stars. The sun is like a huge nuclear fusion reactor, tremendous, almost unlimited amount of energy. Because of the gravity of the sun, the hydrogen are being fused together to produce helium and other, the neutron and other forms of energy, mostly heat and all the range of electromagnetic spectrum. Okay, so it's hard to control this because you need to contain that. In the sun, you don't need a containment because we actually are benefiting from the nuclear fusion of the sun. It produces a lot of energy, heat, visible, a lot of energy. Okay, now let's proceed to applications of radiation in medicine. So as I've said, I'm a medical physicist. So what does a medical physicist do? We apply the concepts and theories of physical sciences to conduct research, develop or improve theories and operational methods for diagnosis, treatment, and rehabilitation. So as a medical physicist, there are actually sub-branches of medical physics. So there is even diagnostic radiology physics, nuclear medicine physics, medical health physics, and radiation therapy physics. I did some residency for radiation therapy physics, but we do have some practicum in diagnostic radiology, nuclear medicine, some medical health. Okay, so let's go to the first one, diagnostic radiology physics. Diagnostic radiology physics. The diagnostic applications of X-rays, gamma rays from sealed sources, sealed radioactive sources, radio frequency radiation, magnetic fields, and ultrasound. So the purpose of diagnostic radiology physics is applying physics to diagnose patients, any forms of diseases, to see what's inside the patient. So we use X-ray. So you will encounter machines such as X-ray machine, fluoroscopy machine, CT X-ray machines, even radio frequency and magnetic. MRI is part of diagnostic radiology physics, and ultrasound as well. So here I did some practicum in Amang Rodriguez Medical Center. These are my pictures long time ago. I think 2000, like I don't know, 15 years ago or 18 years ago, long time ago. So they might have different machines now. So these are the old ones. So this is the CT control console. These are the machines that we used for my undergraduate thesis. So perhaps this is 20 years ago. Okay. So this is the Geiger counter that we use and some phantom to do some tests on the quality of the image. These are the substitute for the bones, for the spinal cord, for the lungs. So we do some testing and alignment tests and leveling tests. This is the MRI, magnetic resonance imaging, which is used to image the patient, usually for soft tissue. This is in UST Hospital, MRI, CT scan. So they have new machines now for CT scan. This is National Kidney Transplant Institute, their permanent magnet MRI, the control console. So these are sample images of diagnostic radiology. This is CT X-ray, CT, computed tomography. So as you can see, the bone is quite clear in the structure of the brain. So see, it's like I think this patient is operated already. Half of the brain is gone. And spinal cord, as you can see the bones and the spinal disc. These ones are MRI images. As you can see, the soft tissues are very clear, but the bony structure are dark. So because of the physics behind, I'm not going to explain, guys. This is general physics, so we try to limit the discussion to simpler, but not simple. If you want to know or learn more, you can ask me or you can search on your own. So as you can see, the soft tissue, the fatty parts, the hydrogenous parts are clear in MRI. Next, another branch of medical physics is nuclear medicine physics. As a physicist, you can go to these fields. So in nuclear medicine, it's mostly radioactive material, the therapeutic and diagnostic applications of radioactive materials, radionuclides. Okay, So both therapy and diagnostic procedure in nuclear medicine. So the key word here is we use radioactive material, radioactive material. So we did some practicum when I did my master's in Capital Medical Center. These are the gamma cameras. There are some procedure that the patient is asked to exercise for some cardiac procedures. And we scan the patient, injected or inhaled, with radioactive material. And that radioactive material usually goes to where the disease part of the body, the tissue, and then we scan it. And here some engineers will do some repairs or maintenance. And here the physicists to measure the radiation outside, surrounding the patient, surrounding the sources. So you have to make sure that we are safe. And we use some devices. This is in St. Luke's Nuclear Medicine Department. This is where they prepare the radioactive materials. Of course, it's lead shielded, so we are not exposed, or the radio pharmacist is not exposed. And this is sample images. As you can see, the cancer spreads to the bone already. We scan it with a gamma camera, or the machine. And this is for the positron emission tomography. This is in St. Luke's. So as you can see, there's some robotic arm here that is used to handle radioactive materials. We are not exposed, and this is the PET scan, the positron emission tomography machine. And here I am holding for picture taking. I'm not actually operating it, but you can see there are some like inside the radioactive material, of course, and there is like another robotic arm that handles the radioactive material. So this is your PET scanner and sample images of the PET scan. So, oops. So take note that in most procedures for nuclear medicine, we can see the function of the functional, we can get functional information of the tumor, of the disease part of the patient. So this seems to take up a lot of, for PET, it takes up a lot of radioactive material, the fluorodeoxy and FDG. Okay, just search on your own if you want to know more, because we don't have time. This is general physics series. So the radioactive material goes to the tumor part of the lung. Okay, it's highly active. But nowadays, the trend is you can actually fuse CT, which is anatomical image, and PET, which is mostly functional. So you have CT scan here fused with PET. It's a little bit blurred spectrally, you cannot see much of the structure. But if you combine the functional and anatomical anatometabolic image, you can see that you can see clearly which part of the tumor is highly active. And there are some parts who are active here on the sides. So perhaps the lymph nodes are active here. Okay, so you can get a lot of information for anatomy, the size, morphology, but no function. But for PET, you can get the metabolism. So if you combine the images, you can get the functional and anatomical image information of the patient. Another sample here, PET-CT fusion. These are PET image. You can see where the tumor is, but it's not that clear where specifically because of unclear structure. But if you combine it with CT, you can now see that, oh, this is where it is. So it's better. Oops. You have the CT scan combined with PET images. Okay. The pelvic area, PET images. You can see the function. It's metastasis already in the liver, abdominal part. But combined with CT is even better. You can diagnose more accurately where the tumors are. Kumalat na. CT, as you can see, there's no information as to the activity of this tumor, but it's already eating up some part of the lungs. So it's a little bit scary already. But as you can see, not all parts of the tumor are uniformly active. Some parts of it are highly dividing or highly active. So perhaps if you treat it with radiation, you melt it with radiation, perhaps you can give more intensity or amount here. Okay? So nowadays it's 4D, even 4D, 4-dimension. As you're breathing, you can see the motion. So anatomy plus fusion, these are now high-tech machines. X-ray, CT, MRI are more anatomical, but PET is more functional. Now, what are the other works or fields of medical physics in the hospital? There's also called health physics or medical health physics. So it's more on the safe use of X-rays, gamma rays, electron and other charged particle beams of neutrons or radionuclides and of radiation from sealed sources for both diagnostic and therapeutic purposes, except with regard to the application of radiation to patients for diagnostic therapy. So usually this is more for the safety of the patient and the staff as well. So we are in medical health physics, we're monitoring the radiation dose received by the medical physicists, by the staff, all the staff, rad techs, doctors who are working in these facilities. So we have to check if they're receiving too much radiation, which they should not. Okay, we should not put our risk for unnecessary exposure. And the last part that I'm going to discuss about the fields of medical physics, applying physics in medicine, is radiation oncology physics or the radiation therapy physics. So it's the therapeutic application of X-rays, electrons and charged particle beams, neutrons and radiations from sealed sources, usually to treat tumors, to treat cancer patients. So like gamma knife. So this is a linear accelerator. It produces highly energetic X-rays. So this one is radioactive material, this one is X-ray machine. So we use radioactive material, it emits gamma radiation to treat cancer patients, to treat tumor, but we can also use much higher energy X-rays to treat cancer patients. So you have here a cancer that is in the nasopharynx, nasopharyngeal area. So the red parts are receiving 100% of the radiation, but the blue part is usually lower dose, 20%, 10%, even 5% only. So we're sparing the normal structures, but delivering the maximum dose or the prescribed dose to the target, to the tumor. And it's CT 3D imaging guided. So here, if you have a case, this is retinoblastoma, there's like a cancer of the retina. So it's very critical because there's a high risk that the patient will be blinded, but you cannot just let it grow. Definitely the patient will die because of that. So we have to treat that cancer. But as much as possible, we have to spare the other lens, the other eyes, and even spare the lens here, because perhaps if the retina can recover, perhaps there's a chance that the patient can still see on this part of the eye. So we have to treat the cancer, the tumor, and still, try our best as a medical physicist to spare the lens and other normal structures. It's a very critical, case. Here you have a child undergoing a whole brain irradiation and spinal cord irradiation. So it means, why are we irradiating the whole brain? So you expect side effects, but the tumor is metastasized already, different parts of the brain, even the spinal cord. So, and that, if you don't stop it, definitely the patient will die or the patient will suffer. So we have to treat those cancer cells, even if it's like micro, we cannot see tumor, but it's there. It's metastasized already. So we're trying to save lives here. Okay, so take note that it's a high-tech environment. So before we deliver the radiation, we double check, make sure it's correct. And there are a lot of experts involved. Alignment is very precise and accurate. You have to make sure of that. There are a lot of professions involved. The neurosurgeon, the radiation oncologist, one of the major professionals here, the medical physicist, the radiation therapy technologist or the rad techs who delivers the radiation, the medical physicists, we do the treatment planning and do the quality assurance of the machine, of all the devices there that we use. The doctors, the radiation oncologists prescribe the dose and sign if it's the correct plan, if it's the right plan for the patient. So there's a lot, it's a team of professionals. We have a lot of trainings for this. Okay, so that's all. So in a way, physics saves lives, Of course, there are negative and positive aspects of radioactive materials and radiation, but we use it to save lives. And that's the purpose of medical physics. Thank you guys, and I hope you learned something from this lecture. Bye bye. Choose.